Hello class, how are you? Today we are going to a new chapter called vector field. Well, I'm sure we study vectors throughout Calculus 3 and we also study vector value functions, which vector value functions are used to define a path that for the I component and the J component and the K component, if it was in the space, we assign a function to each of these components, and if it was the plane, we just had I component and the J component. And we talk about the smooth curve, and also we represent that vector value function for every t value a position vector. Like if I had 2 square I plus t plus 5j and plus t cubed minus 1k, at the t equal to 1, the position vector was 1, 6, and a 0. That represents the position vector to that point, which my x was 1, my y was 6, and my z was 0 at the t equal to 1 to get to that point. Then at t equal to 2, I got to 4, 7, 8 minus 1, and a 7. And at t equal to 2, I got to that point, and that create me a path. And we talk about the smooth curve, that the f prime of t, g prime of t, h prime of t cannot be simultaneously equal to 0, and many more things. Today when I talk about the vector field, means I am giving you a field, just like a cornfield, just like a cotton field. I'm going to assign a vector to every one of those points. The field could be a plane field, or it could be in a space, either in R2 or R3. And every one of point you have a vector, but there is no guarantee that those vectors have same direction or they have same magnitude. Okay, let's put vector field aside for a minute and let's talk about a function and say that function is x squared y plus 2x minus y cubed. And if I take the gradient of that function, the gradient of that function respect to x, and this is an R2, is 2xy plus a 2, and respect to y you have x squared minus 3y squared. Please let me know, for every point on the plane, such as 0, 0, if I replace x by 0, y by 0, what do I get? I get 2, 0. Don't I get a vector that is assigned to 0, 0? What happens if I go to 1 and 1? Put 1 and 1 right here. I get 2 plus 2, 4. 1 minus 3 is a negative 2. Therefore, you get 4 and a negative 2. You go 4 this way and you go negative 2 that way. I do assign a vector to that point too. I can assign a vector right here. 0, 1 is 2 and negative 3. 2 and a negative 3. I can assign a vector right here. Therefore, I can assign a vector to any ordered pair inside that plane. That's called a vector field. Therefore, you're going to say vector fields is the gradient? I didn't say that. I said maybe we can use gradient as example that represent a vector field. And in here you said, why did you say not all the vector fields are not gradients? Number one, a vector field, vector has magnitude and has direction. In R2 you have 2 components, in R3 you're gonna have 3 components. I'm gonna make X and Y to represent my R2 as 2 variables and XYZ as my R3. Therefore I'm going to put Y here and I'm going to put X in here. That is a vector. For every ordered pair in a XY plane, I am going to have a vector field. I'm going to have a vector. Therefore I call this one a field full of vector. That's the example of a vector field. The notation is a bold-faced letter F. And in here I can put XY, I can put YZ, and in here I can put X and Y and Z. That's another example of a vector field in R3. Okay, but you're gonna say this is a gradient, this is a gradient. I said I didn't say these are gradient. I said these are vector field. Vector field. Do you want to call it a gradient? Welcome to do so. That's the gradient of some function is y comma x. Then if this is the gradient, would you please tell me the function that this is its gradient? You said yes. The function is, that's the lowercase letter f, is not a vector field, is xy. Partial derivative with respect to x is y, partial derivative with respect to y is x. I said okay, I understood. Then from today I'm going to say yes, this is a gradient, and you were able to take, you find the function. This is called a potential function, a function that this is its gradient. Therefore, yes, you can call that gradient an example of a vector field. But I'm going to write another one right here, an easy one for you. Negative y and x. I said this is a vector field. That's the vector field. Give me a function that this one is gradient. Okay, and you said you want to call this one a gradient. I said perfectly fine. Give me a function that this is one is its gradient. Somebody said this is the partial derivative with respect to x, therefore it's negative yx. Partial derivative with respect to y, that's the xy. I'm going to combine these two because these are not the same, and that's becomes 0. Are you telling me the gradient of 0 is this? Sit down and think for 2 or 3 hours. Can you give me a function that this is one is gradient? I don't think I can. Therefore, I'm going to say this is not a gradient because you cannot find a potential function. But this is a vector field. It is a vector field, but does not represent a gradient. Gradient is an example of a vector field if and only if you be able to find its potential function. Then if you be able to find its potential function, that gradient can be represented as a vector field. In here, this is a partial derivative with respect to x. That's x squared over 2y. That's the partial derivative with respect to y, is y squared over 2z. That's the partial derivative with respect to z, is xy z squared over 2. If these are in these three antiderivative, if all repeated and they are the same, you write it once. If it's not, you have to combine all of them and say, yes, I find the antiderivative. This doesn't look like this. This doesn't look like this. This doesn't look like this. And I'm going to say, okay, if you consider this one the function, is the gradient with respect to x is this? I'm going to say no, because this is 2xy over 2. You also have another x in here, and that should be with respect to x only. Therefore, this is a vector field, but is not a gradient because I cannot find the potential function. Then from today, vector field is a plane or it is a space that you can assign a vector to every single point, and gradient is example of a vector field if only and only you can find the potential function for that gradient. If you can find the potential function, you can call that gradient a vector field. And if you cannot find it, that one is a vector field, but you cannot call it gradient. Somebody said, explain it one more time. I said a vector field can be called gradient of some function if you only can find a function that is gradient, it look like the vector field. That function is gradient is this, therefore I call that gradient a vector field. Then somebody said, number one, what is the gradient? Gradient itself is a vector. And we always said gradient is always normal to the level curve in the previous lesson, and the gradient is always move in what direction? In a direction of the fastest rate of change. Therefore, if you see a tornado is moving in a fastest rate of change. It's not going to go that way and that way. If you look at those tornado people chasing the tornado, you see they pick a path that they can travel the fastest. Hurricane is changing direction all the time. And also we find out, yes, a gradient has a direction, also have a magnitude, and that magnitude is in the direction of fastest rate of change. Somebody said, okay, but if you give me a gradient or a vector field, how am I going to build the field? How do I know if my field is like this? How do I know if my field is like this? How do I know if my field is like this? How do I know how does my field look like? Maybe your field is a circular field. Maybe it's a parabolic field. Maybe it's a field that is like a function a square root field in going in that path. This is nothing except a tornado. and that has a magnitude and direction at any given time. Please note, if you have a gradient has a magnitude. And what is the magnitude of the gradient? Is the square root of y squared plus x squared. And what is a magnitude? Magnitude is a scalar quantity. I can call it a C. Then can I graph the level curve? Said yes. When the C is 0, you have a point. When the C is 1, you have to square both sides, you get a unit circle. Somebody said, well, what happens if the C is 0.1? You have this level curve. 0.2, you have that level curve. 0.5, you have that level curve. Therefore, you're going to have infinitely many circles. Maybe for 2, you have a bigger, this one for a 5, you have a bigger. These all create you with infinitely many circles, and all are what? Are going to be filled with circle. You shouldn't have any white spot in here. All should be black, and it should be like a what? Plain field, like a cornfield. You'll be able to allow to put the seed at any location you want. I said, okay. What happens if this one is a circle with a radius of 2? Therefore, that point is 2 and 0. Would you put that 2 and 0 inside that gradient? Y is 0. I'm sorry. X is 2. Therefore, your y become 2. And your y is 0. Therefore, at that point, you have a vector field which is going to become 0 and 2. And what is 0 and 2? Right there. What happens if I pick this one right here? That becomes 0 and 2. Therefore, your x is 0, y is 2. That's 2. Do you see this is 2 also? This is 2. Somebody said, what happens if I pick a point right here? I don't know. Give me, if I put the square root of 2 plus a square plus the square root of 2 squared, that become 2 plus 2, 4. Oh, I'm going to put radical 2 over 2 and radical 2 over 2. Then it becomes radical 2 over 2, radical 2 over 2. What is radical 2 over 2, radical 2 over 2? Is 0.74, 0.74. You have that vector. Oh, that vector is the square root of 2, square root of 2. Let me see what is magnitude. Its magnitude is 2 plus 2, and it's 2. Oh, it's the same magnitude as that one. Then are you telling me that every vector in this level curve, they're going to have different direction and they have same magnitude? You better believe that. Every vector right here is going to have same magnitude, but it's going to have a different direction. I can do the same thing here. Same magnitude, same direction. Can I assign a point, assign a vector to every ordered pairs here? I can say yes. That is called a field full of vectors. But somebody said, you said it as an instructor, some of the gradient can be gradient is an example of a vector field. Yes, gradient is a vector field. But not all the vector field are gradient. Not all of them are gradient. Then what is the difference between these two vector fields? The one of them which can be a gradient and the one which cannot be a gradient because you cannot find the potential function. The one that it can be the gradient means if you have a gradient and you can find the potential function, that gradient is a vector field, and that vector field called conservative. Remember, every day they ask you conserve energy, please. That's the word from physics. Conserve energy. But the one of the force field, the vector field, which cannot be represented as a gradient, that called non-conservative. What does that mean? These vector fields use lots of electricity. They don't conserve energy. They waste energy. They waste electricity, but they don't. What I mean by conservative means if that is you and you come to my house and be my guest and have a lunch, you gain some energy. You said, okay, at this point, you are 20 feet above the earth. You have a potential energy, and this is mgh, your weight times h. Conserve means whatever energy you have here, please, don't lose it if you go here. Well, somebody said, well, I go here, my potential energy become less. I said, yes, transform it, change the form of the energy. Here you have potential energy, not as much as that one, but you gaining kinetic energy. As long as your potential energy plus kinetic energy stays same throughout this traveling, means you're not losing the energy, means you didn't waste my lunch. When you get here, your potential energy becomes zero, but your kinetic energy is as much as the potential energy right here. That's called conservative, that the sum of the kinetic and potential energy always stay the same. They conserve energy, they don't lose energy. And these are called conservative forces. And somebody said, what is a conservative forces? Conservative forces is here, if this is Amazon and this is your house, if you tell Amazon, please bring me a package. If Amazon is a conservative force, they can bring you this route, they can take 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 this route. It doesn't matter which route it take. As long as Amazon is a conservative energy, the amount of work is the same throughout all this path. Therefore, they're going to say, if you are conservative, you are independent of the path. But if the Amazon is not conservative, the amount of work here is way more than here, and is way more than here. Therefore, if Amazon is conservative, doesn't matter which path you take, all of them charge you same amount. But if the Amazon is not conservative, in this one they charge you $10 because they have to do more work. In here they charge you $8 because they have to do less work. In here they charge you $4 because they have to do less work. In here they charge you $2. And I'm hoping Amazon become conservative. These are example, analogy. Then become independent of the path. Let's talk about some of the conservative forces. Number one, if we talked about, maybe, let me think, let's talk about velocity field. We talk about the velocity field. Okay, you could have a pipe, water goes through here. But the speed of the water at every location is not the same. Some part is faster than the other one. Therefore, you have all of these vectors are horizontal if the pipe is horizontal, but some of them, they have a bigger magnet than the other one. Because this one is by the lot of residue here, there is a barricade here, it doesn't let the water run, there's a lot of algae here, and so on and so. Same thing at the river. At the middle, the water travels the fastest. Therefore, that is a velocity field. Therefore, if you have a boat and you go in the river, you really like to go in the middle because you have the force of your boat, the force of the motor you have on your boat, and also you have the current. They take care of it and you go faster. Or traveling the airplane with the wind, not against the wind. And they have different magnitude. Or how about if you think of a tire of your car? At the center is connected to an axle, but there are infinitely many points on your tire. But all of these points had to get back to your initial position at the same time. Therefore, if you take 1 minute for this tire to rotate, all of these points have 1 minute. But this point doesn't go anywhere. It is exactly in its point. Then the velocity is 0 right there. But this point, boom, it doesn't have to go much because the circumference is less. Circumference get more, circumference get more, circumference get more. Therefore, the particle in this one must travel much faster than the particle on that one. And this must be this one, and this one is that one, and this one is that one, and this one is this one. Therefore, this is an example of the vector field. At every point, the vector does have different direction, but as long as they are on the same level curve, the magnitude is the same. Well, let me take this one and say maybe this is the Earth, and this is the center of the Earth. And center of Earth, there is a mass in there called M2. And there is another mass at the point of X, Y, and Z. Can be anywhere. Therefore, there is a force of attraction. They two attract, and maybe that M1 is attracting by M2. And what is the distance between these 2 points? X2 minus X1, Y2 minus Y1. This is located at 0, 0, 0. And Z1 minus Z2. That's your distance. Then you do know the force on the Earth respect to the center is always indirectly proportional to the square of a distance. Therefore, this is K over X squared plus Y squared plus Z squared. Means as you get further and further away from the center of the Earth, you get lighter and lighter and lighter and lighter. Because that distance gets bigger and bigger and bigger and bigger. The fraction gets smaller. Then the force of attraction between these two is M1, M2 over X2 plus Y2 plus Z2. But there is a gravity that it brings these masses together. That's the constant of proportionality. But because the distance decreases up with a negative. That is a gravitational, the Newton's law of gravity. But somebody said, if I'm here, I go that way. If I'm here, I'm going that way. If I'm here, I'm going that way. Therefore, I have a path here. And what is my path? My path is xi plus yi plus, j and zk. This is called a position vector. And it's going to be the same for all of them in that path. Therefore, this direction and this direction and this direction and this direction is different. Therefore, I have to tell you where the M1 is. Therefore, I do have here a magnitude, but I just need a direction. Direction, I'm going to do a unit vector. And that's called a vector field. But somebody said, what is the unit vector? Your unit vector here, it could become r of t over the magnitude of r of t. That's the unit vector. But somebody said, if I write f of x, y, and z, and if I write g m1 m2 divided by x squared plus y squared plus z squared, and a negative, what happens if I change this one and change it to a letter C and make this one a Q1 and make this one a Q2? Then Q represented a charge. This is a Coulomb's law. Coulomb's law is also example of a vector field, but I do need a unit vector, and you can put your unit vector, the unit vector for the position function. Therefore, if you're talking about gravitational, please note that distance right here is more than that distance. And as the distance gets bigger and bigger and bigger and bigger, right here, the distance gets bigger and bigger and bigger, what happened to this value? It gets smaller and smaller and smaller. Therefore, in here, my vector is going to be much smaller than this one, and smaller than that one. As I'm going away from the Earth, that vector getting smaller, and this vector, and this vector, and that vector, and that vector. Therefore, I can have an example of a force field right here. And what do they call that? They call central force field, because everything attracts to a center. And these are conservative forces, because conservative forces conserve energy. They change it from one form to another, but they do not waste it. Then if I have a force field, and the force field is 2y comma x. First, let me see if this could represent by a gradient. I'm just asking if this could represent by a gradient. Therefore, if I assume this is a gradient, that should become a partial with respect to x. Therefore, that should become 2yx. And this should become partial with respect to what? Respect to y. That should be xy. Therefore, partial with respect to y is x, and partial with respect to x is this. Well, are they similar? That's two of them, that's one of them. If there was only one, you can copy one. But that's two of them. Let's make it, I have to write both of them, and that make it 3xy. And when I take the partial with respect to x, that becomes 3y, and respect to y. Therefore, that vector field does not represent a gradient. Therefore, that is not. That is a force field, but it's not a gradient. Therefore, this is not a conservative. That's a non-conservative. Somebody said, "You kidding me?" I said, I give you a reason. Let's start from a function itself. I said that function is x squared y plus 2x plus 3y. We're going to cheat. We're going to start from that function, and we're going to create a vector field. I did say vector field might be a gradient, but all the gradients are vector field. I said all the gradient are vector field, but not all the vector field are gradient, because you cannot find the potential function. And some books, they call the potential function phi of xy. Some books call it f of xy. Therefore, these are called potential function. Whenever I said potential function, you can represent it with any letter or any letter you want. Well, I want to create a vector field right here. Give me the partial with respect to x. That's 2xy plus 2. Partial with respect to y. X squared plus 3. This is a gradient, and that gradient is a vector field. How do you know? Because I got it out of that function. But what happens if I give you this gradient, and if I give you that gradient and said, okay, this is a vector field, this is a vector field, I don't want to go in the headache of finding the potential function, but looking at it, tell me if these are conservative. Oh, by looking at it, yes, you can. What is this? That's partial with respect to x. Would you differentiate it again respect to y? Respect to y is 2x. this is respect to y. Would you give it to me respect to x? Because we said order doesn't matter. That's 2x. Is f of xy is equal to f of yx? Yes, that's the proof for conservatism. If f of xy become f of yx, therefore that vector field is a gradient and it is conservative. Well, let's look at this one. That's the partial respect to x if I consider this one a gradient. What is respect to y? 2. That's a partial respect to y if I assume this is a gradient. What's the partial respect to x? 1. Are they the same? No, that's not a conservative, and it is not represented by a gradient. But somebody said, okay, this is a vector field. Can you graph the vector field for me and show me the field? I said yes. First you have to find its magnitude. The magnitude is 4y squared plus x squared. The magnitude is a scalar, call it a c, and this is 4y squared plus x squared. Start plugging number for c. That's elliptical. If c is 0, you have a point. What happens if c is 1? You have 4y squared plus x squared. I'm going to divide it everything. This is a 1. I'm going to divide it because this is a 4, but this has to be a 1. I'm going to make it over 1/4. Therefore, you have x squared plus y squared over 1/4. See, I just moved the 4 down the stairs because the right side is already 1. Therefore, what is your a? Plus minus 1. And what is your b? Plus minus a half. That's the level curve. I bet you can do another one when c is 2. I bet you can do another one when c is 3. Therefore, in here you can pick point here and start filling up the vector for it. But all you need is 3 or 4 vector right here, or 5 or 6. But it shows you the orientation and the vector field and things like that. Then, if someone asks you that I do have a vector field of 2xi plus yj, and I said this is a vector field and that should be a bold face. Is this conservative or non-conservative? What is the partial derivative with respect to y? 0. What is the partial derivative with respect to x? 0. That's conservative. Then I'm going to ask you right away, give me the potential function. That's 2x squared over 2 plus you holding the y constant. What is for that one? Because you undid respect to x. You integrate this one respect to x. You integrate this one respect to y. You holding the x constant. You add both to, if they are the same, you write it once. If it's not, you write it, all of it. And say that is your potential function. Right now you want to call it phi of xy, f of xy, and somebody said, okay, that is the mother function. What is this gradient? Respect to x is 2x. Respect to y is y. That is a potential function. That is a conservative force, independent of the path. You can find the potential function, and in the future, if I ask you to integrate that, since you can find this potential function, it's easier to integrate, to do this than that one. Then, also, something else I was going to say right here before I say bye, about this one, and if you want to check it, you have to do the order, and this one is telling you if this is conservative or that's not conservative. This has a counterpart. And the counterpart of this one is this. What is this? This is a tornado. Tornado has a curl. Therefore, some force have curl. They rotate. Some of them are curlier than the others. And at every point, you have a vector that vector is going to have, every one of those vectors have different direction. On next video, we're going to talk about the curl of the function. And from there, we're going to see what is the relationship between these and these, and how we can use curl to determine if the force is conservative or not. Thank you.